Okay, 7.6 applications of the cross product. So let's look at a few applications of the cross product. So the first one is going to be about torque. So here we have an example where we have a force of 60 newtons applied to a wrench in a counterclockwise direction at 80 degrees to the handle, 20 centimeters from the center of the bolt, and we're asked to calculate the magnitude of the torque. So torque, as a physics term, is defined as a cross product between two vectors. The vectors that represent the distance to the center of the bolt and the force vector. Okay, the the um, the result of the torque is itself a vector that acts in the direction of the bolt. Right, so either you're tightening the bolt or you're loosening the bolt, and you can, as you can imagine, that action is perpendicular to the displacement, the r vector and the f vector. Okay, so something like the cross product would be more appropriate to use for torque than something like dot product, right? Dot product only produces a scalar. Okay, so the torque can be calculated, well, the magnitude of the torque can be calculated using our cross product formula, which is given as the magnitude of r times the magnitude of f times the sine of the angle between the two vectors. So the torque for part A is simply, the magnitude of the torque is equal to 0.2, which is the length of r. So I'm converting 20 centimeters to meters. So 20 centimeters is 0.2 meters times 60 times the sine of, so the angle between the two vectors is 80 degrees. So you can see here in the diagram it's 80 degrees, whether they're head to head, but even if you were to draw them tail to tail, that angle is 80 degrees. Okay, so sine of 80 degrees, and when I calculate that, that answer is 11.8 Newton meter. So the reason why I converted the centimeters to meters is just an SI unit, like the international standard units we're using here is a Newton meter for torque, um, and that's how it is. Okay, so part B, in what direction does the torque vector point? So again, if you are using the right hand rule, right? So if it's going to be r cross f, you're taking r, you're pointing your fingers toward r, you're swinging them toward f, and the direction of your thumb is into the page. So the answer for the direction is that it is going into the page. And then, realistically, does that make sense? It sure does, right? So, if you're twisting a wrench going clockwise, right, what's happening to the bolt is that it's tightening, right? So the torque is going into the page, which means the bolt is tightening and it's going deeper into the hole that it's going into. Okay, so that's kind of like how you can really connect it to a real life situation. And bolts generally tighten when you turn them clockwise. Okay, so that's just one example of torque, one of an application of cross product. Okay, example number 2: determine the projection and its magnitude on of A onto B, given that A is one vector there and B is another vector, given its components. So not so much cross product, but again, a reminder of how we calculate projections, right? So projection, so it's a good example to just kind of get you to think about, okay, when you get a problem, what formulas do you need to use? So here we have the projection of vector A onto B, which is equal to A dotted with B divided by B dotted with B, and that acts that's your that all of that is your scalar value k in the direction of b, right? So it's just the projection is um, how much of vector b is acting on that. Oh, sorry, how much of vector a is acting in the direction of b. All right. So if I calculate the dot product of the first part, a dot b, I would take the algebraic dot product, so -4 times 5 for the x components plus 1 times -3 for the y components plus negative 1 times 9 for the z components, divided by b dotted with b, well, b dotted with itself, so it's each component, so 5 times 5 plus negative 3 times negative 3 plus 9 times 9. And that, again, is in the direction of b, which is defined as the vector 5, negative 3, and 9. Okay, and then if I simplify the scalar component, the scalar part of this line, we get on the top negative 20 minus 3 minus 9 all over 25 plus 9 plus 81 in the direction of 5, negative 3, and 9. And then we can simplify that to get negative 32 on the top over 115 on the bottom, multiplied by the vector 5, negative 3, and 9. Okay. Now I take that scalar and I multiply that into each component of the vector. The resulting vector is then negative 160 over 115, comma 96 over 115, and negative 288 over 115. And then if I simplify this into lowest terms, I could do that too. I think the top and the bottom can simplify to negative 32 over 23, but the other ones I believe will remain as a fraction out of 115. Now this step is not entirely necessary, but can be useful. And then I do want the magnitude, so determine the projection and its magnitude. So we have the projected vector here. Okay, so this is the vector that acts along the direction of b. And that vector, I want to find the magnitude. So the magnitude of the projection of vector A onto vector B is just the square root, applying the Pythagorean in 3 components. So negative 32 over 23 squared plus 96 over 115 squared plus negative 288 over 115 squared. And then that will, once simplified, gets you this. Well, the inside is square root of 1024 over 115. And but moving on to the next one, example number 3. Given vector A, negative 2, 1, and negative 6. Vector B is also given, and vector C. Evaluate something called the triple scalar product. A dotted with B cross C. Okay, so here, now you have to be careful. There's a specific order. Now, in multiplication, usually the order doesn't matter. But here, in this case, with vector multiplication, order does matter. So remember, A dotted with B produces a scalar, okay? And you cannot do a cross product. Well, a cross product must have a vector crossed with a vector. So you can't do a scalar crossed with a vector. So that order does not work. What you got to do is do B cross C first, which is going to result in a vector, and that vector can then be dotted with vector A. Okay, so here we have vector B cross C is what we're going to do first, and so I'm going to follow my method for doing cross products. I'm going to write vector B 2 times, so negative 3, 4, 8. 3, negative 4, and 8, 3, negative 4, and 8, and vector C, 5, negative 2, and 7, 5, negative 2, and 7. Cross out the first column, cross out the last column, and then do my cross multiplication and subtractions here. So B cross C will be equal to negative 4 times 7, which is negative 28. Take away negative 2 times 8, which is so I make that as plus 16, and then 8 times 5 is 40, minus 7 times 3, which is 21, and then 3 times negative 2 is negative 6. Take away 5 times 4, which is 20. And so there we have vector B cross C. When I simplify that, we get negative 20, negative 12, positive 19 for the y component, and positive 14 for the z component. So that B cross C gives you the vector that we need so that we can do a dot product with vector A. So vector A dotted with B cross C is going to be equal to, just take the x component of vector A, -2 times the x component of vector cross product, -12, plus, repeating for the other components, 1 times 19, plus -6 times 14, and then the resulting answer when you multiply and add all these terms is -41. So there's what we call the triple scalar product. So it's a triple, there's a three things being multiplied, but the final result is a scalar value because the dot product gives you a scalar value. Okay, part B, determine the volume of what we call a parallelepiped. Parallelepiped. It's hard to pronounce the word, but what essentially it is just a parallelogram being extruded into this kind of prism-shaped object. Okay, and it turns out the volume of this object is equal to the absolute value of the triple scalar product, the same kind of calculation we just did. Okay, so think about, okay, what's the volume of, in general, what's the volume of a 3D shape? It would be, the volume is equal to the area of the base times its height or its depth. And so the area of the base we're considering here is the bottom part of this 3D shape, and we're going to need to determine the height to find the entire volume. Okay, so anyways, it still hasn't changed the idea that it's the area of the base is still a parallelogram, and the parallelogram area is just the cross product of the two vectors that make up that parallelogram. So the vectors that make up the parallelogram are u and v. So u cross v, that magnitude will be the area of the base. Okay, and then the height of the prism h. Okay, so that's not going to be the slant height; it's going to be the perpendicular height. Okay, so let's just erase some of these markings there. So the perpendicular height, it's related to vector w. Okay, so you have vector w here making a right angle triangle. Okay, so the perpendicular height, if we look at this right angle triangle, would be w. Let's solve it right here. So the magnitude of w times, we're going to define theta to be up here, okay? And if we said theta was up there, then it would be w cosine theta. Okay, right? So just to remind ourselves here, so cosine theta is equal to the adjacent side divided by the hypotenuse. So h divided by the magnitude of w. And and that's when we rearrange it, so h is equal to w cosine theta. Okay, so what we have here is a cross product, a u cross v, and then we have that, and that produces a vector, and that vector has a magnitude multiplied by another magnitude w times cosine theta, and that's related to the dot product, right? So essentially I can rewrite this volume formula as the magnitude of u cross v, and that produces a vector, and if I dot that vector with w, I get the volume of this parallelepiped, right? And so again, I just condense these two magnitudes times cosine theta into a dot product of one vector, which is the result of a cross product, to dot it with another one, w. Okay, so that's the idea. That's how we come up with the formula for the volume of a parallelepiped. Okay. Example 4, we have another application of cross product here, a simpler one, I would think. A vertical force, Ff, of 500 newtons is applied to the pedal of a bicycle. The pedal is attached to an arm that is pivoting around point P. If the pedal arm is 15 centimeters, what is the magnitude of the moment about P in each case? Okay, so this, another little physics thing you got to know if you haven't been studying physics much. Then they'll just have to define it, and you have to kind of take it on face value. And so moment is kind of like torque. you are looking for a vector, the magnitude. It's the result of the cross product of two vectors, r cross f. So we have the force applied on something, and you have a length of an arm, like a radius, and instead of torque, we're just calling it a moment. And so let's just define that. So the magnitude of the moment vector is just the magnitude of r times the magnitude of f times the sine of the angle between the two vectors, sine theta, right? The moment, just like torque, acts in perpendicular direction to the other two vectors. So there are three different cases here. So if we look at the first case where the pedal is horizontal, so you kind of have to like draw this out a little bit. Here the pedal is acting directly to the wheel, so you have a little arm there, and you have a pedal on the bicycle. It's represented by that. And let's say your foot's on the pedal. They're applying a force of 500 newtons, and the radius of that arm is 15 centimeters. Okay, and let's draw that. If you draw it like a vector like this, yeah, you can draw it like a vector like that. And if you could translate forces, right? I can draw that 500 newtons as a force over here, just to signify that hey, I got a 90-degree angle between my two vectors. Okay, and so if I have a 90-degree angle between my two vectors, I have moment magnitude that corresponds to an angle of 90 degrees. So if I carry out this calculation, I have the magnitude of r, the pedal arm, which is 15 centimeters. Again, I'm going to convert that to meters, so that would be 0.15. And then the magnitude of the force, which is 500 newtons, times the sine of the angle between the two vectors here, which is 90 degrees. And the result is a moment of 75 Newton meters. Yeah, okay, and then part B says the angle between the force F and the arm is 150. So let's say I have the arm here now. Here's my pedal, and I'm still putting 500 newtons on that pedal, and the 15 centimeter arm is still here. The angle now between the two vectors is 150. Okay, and so that just adjusts the moment calculation. The moment is equal to 0.15 times 500 times the sine of 150 degrees, and then that is going to give you a moment magnitude of 37.5 Newton meters. And then finally, the angle between the force F and the arm is at 60 degrees. So let's say now we have the pedal has changed locations once again. Here it's down here where the force is still acting downward at 500 newtons, and my 0.15 meter arm is still here, and the angle between the two is now at 60 degrees. And then the result is going to be the moment equals 0.15 times 500 times sine of 60, which is 65 Newton meters. So a little bit more of a moment as the angle between the two gets a little bit smaller. Okay, so those are just again recapping what we've looked at here. We've had applications of the cross product. One of those applications is torque, and the torque of a vector is acting perpendicular to the first two forces given to you. And then we had another example on projections. So I mean, this one's not particularly cross product, but it is in the textbook. So we did another example here, and you'll find another example 2 in the textbook section for 7.6. And then we looked at triple scalar products. Here we have a triple scalar product, as well as the application of a triple scalar product, which can help you find the volume of a parallelepiped shape. And then And so yeah, I didn't mention, but yeah, parallelepiped is just like it's a rectangular prism, kind of like, but the you got all six sides, which each side is a parallelogram, right? So that's a parallelepiped. And then we have an example on the application of forces acting on uh, a pedal of a bicycle. Okay, so a concept called moment, which is very similar to torque, if you want to think of it that way. Um, and yeah, and that would come up with in some of the textbook problems. Okay, and if I'm not sure if my diagram is not entirely clear. Just so we're clear, what's happening with moments in a bicycle. Maybe I should have drawn this diagram to begin with. But yeah, if you have a bicycle pedal, uh, what's happening when you're turning the wheel of a bicycle, right? So the force that you apply, and then here's the r vector. What's happening is that the force you apply is generating a moment. So kind of like that twisting motion on the torque on a bolt. It's going in and out of the page. Just like the moment is kind of like, well, you're either going to be generating a moment that's going clockwise or it's going to be going counterclockwise, uh, and that's how that could be visualized, right? Because you're generating a rotation of an object based on these two vectors, the force vector and the r vector. Okay, and so that's it. I'll be stopping the video.